Great. Let's get started. I'm Svante. I used to work at DevoTeam. I'm currently at Refined. And this is my talk about why Postgres is probably all you will need, or for most use cases. First of all, just to get us started, do we prefer light mode or dark mode? Hands up for light mode. Hands up for dark mode. OK, dark mode wins. Great. So my main sort of thesis is that Postgres is probably one of the most frequently used and simultaneously one of the most underused technologies. And by this I mean that a lot of people use Postgres, but they don't use it to its full capabilities. I'll go through some basics first about the history of SQL and Postgres, and then we'll dive into some interesting use cases. So SQL was invented 50 years ago, so it's a great year for it. It's a declarative language in that you specify what you want and not how to get it, which lets the database decide sort of what's the most efficient path to get the data. And it does that based on both indexes that you've created in your code, but also based on statistics of how previous queries have been planned. And a basic example of a SQL query, I'm sure most of you have seen this, but select star from my table where my column equals and some value. So it's very plain text English-like, but yeah. And as for Postgres specifically, it started in '86 with a completely different query language. It added support for SQL in the '90s. And it's following sort of a correct first and then features and speed philosophy, which is a bit different than many other databases which focus on performance and try and get shortcuts to get faster or more features, whereas Postgres sort of is, we need to get it right first, and then we can focus on performance and features. It's got a great documentation and community that's very helpful, both in mailing list and Slack and similar. One thing that sets it apart from many modern databases is that it's fully open source and non-profit, so it's not controlled by any single company. Many other databases these days are what's called open core, where they have a free version, but to actually get a production-ready version, you need to pay up the enterprise fees. And it's also now used as a basis for many other databases, either directly or as a protocol, sort of other databases using the protocol to be able to reuse clients that are Postgres specific. The examples I'll go over is, we'll start off with an extremely basic key value store just to get us started. We'll talk about full text search, graph and tree queries, document queries. We'll talk about how to quickly get an API server up and running, and sort of how to do in-database authorization. So let's start with a simple key value store. Of course, this is just a table with a key column and a value column. Nothing complex here. If you need better performance and don't exactly care about data durability long term, you can also have it be unlogged, which means that if the database server crashes, it will lose the data, but it's durable in normal operations. So you can gain some speed by treating it more like an in-memory cache, sort of like Redis would be, instead of durable ACID data like the normal default is. So let's go on to full text search. Full text search is what you'd usually use something like Elasticsearch for. So it allows for fuzzy queries where you don't have exact matches to exact phrases within the text of the database, but still sort of get the gist of what's meant by the query to extract relevant documents. In Postgres, it's multilingual, so it has built-in support for 29 languages, and more can be added by adding standard dictionaries. These are the same dictionaries that are used by many other open source tools. It's Hunspell and similar dictionaries, so there is a great number that can be added. It has configurable ranking, so you can weigh individual columns or parts of documents that you find are more important. So for example, you might weigh a title higher than the body of a text. There are helpers to help parse different types of data into text search vectors. So this is what you would use to take the text within the database and turn that into a search vector that can be used within full text search. The primary ones are 2tsvector, which just takes any text document and turns it into a search. And we have JSONB to tsvector. So if you have a lot of JSON documents within your database and you need to, you for example want to exclude keys from being matched within a query, or you don't care about the numbers being part of the search document, then you can use that with a couple of options on how to handle those parts of the document. We also have helpers to parse different types of queries. So this would not be the text within the database. This would be the incoming query from, for example, a user. Here we have a few different ones. The most interesting one is web search to TS query, but I'll talk about these in detail a little bit later. We also have different types of indexing that have different pros and cons to help us out. Some indexes are larger and slower, some are smaller and faster, some take longer to build, and so on. And I'll go through a couple of those options too. But first, let's talk about what this language parsing that we need to do actually is. And one part of it is called stemming, and this is trying to find the root of a word. So it's removing inflection, usually pluralization and similar, to get at sort of what's the root of the word, what's its meaning within the sentence. So here we have some examples where it's removing the inflection, or it's removing the plural of cats into just cat, for example. We also have stop words, and stop words are usually not that semantically relevant to the search. Usually you want just the sort of words that actually mean something within the sentence, and you want to remove the and so on. So the example here is we are getting better now, gets shortened down to just get better, and then it gets matched by that within the database. So sort of because of this, full text search requires understanding of the language of both the stored text and the query. Because of course, different languages have different rules for pluralization or for inflections and so on. We have a couple of different operators that can be used in full text search queries. And, or, and not are probably quite expected. We also have followed by, which means that a certain word needs to come after a certain different word. And we have followed by with distance. So that just means that word A needs to be 2 words away from word B. Those query helpers I mentioned, we have a couple of different ones here. 2ts query takes in basically a prepared query with the operators included, but then it removes the stop words and similar. In all of these examples, I've specified English as the language, but that can of course be a parameter. We have plain 2ts query, which takes in any text string and just converts it to a ts query. Phrase 2 tries to match an exact phrase instead of sort of doing. So you can see here, we have the distance operator between cute and cat. It says that cat needs to come after cute, but it doesn't say any specific distance after. And then we have the most interesting one, which is the web search to TS query, which is meant to be sort of similar to how many search engines works. So people who have good Google foo will probably know these, but for example, you can see that the quoted text gets a distance operator, so we know that sleep and bed needs to be exactly 3 words away from each other. And it's also understand the minus rats, which means that we don't want any rats within these results. It's also understood or to mean that we want those 2 words to be separated by the or operator. So that's usually a pretty good experience if you just want to take user input from a search field and just execute a search directly. When it comes to indexing types for full text search, we have a few different ones. We have RUM, which is probably the best performing one. It's not built in by default. It's an extension, so you need to install it separately from Postgres. But it's really good and flexible. Gin is pretty good. It's built in. It can't be used for ranking, though, which means that first the database needs to pull out all the documents matching by using the index, and then it needs to rank those manually. So it's a bit slower in that process. If you have a lot of matched documents and you only want to show the top 10 that are matching it, then that can be quite a slow process. And GIST, its main pro is that it's smaller and it's faster to build. But it can be a bit lossy, so you need to sort of rematch against documents that have been matched by the index. And it also can't be used for ranking. Here we have how you create a RUM index in these examples. If you've used Postgres, this is probably very familiar. You specify which index type with using RUM in this case, and then you specify which type of operations you want the index to use, which is the RUM TS vector operations, because the RUM index can be used for other things besides full text search. Or, of course, if you store the language in a separate column, for example, you have documents within the same database that are in different languages, you can specify to use that column within the index creation. This is an example query. So we do the normal select star from my table. In this case, I've also included the web search to TS query result within my from clause. And then I use that with the @ sign in my where clause to say which documents match. And then I use the spaceship operator, as it's called, to order these documents by relevance. As a demo of this, I've loaded a database with around 300 gigabytes of subtitles. So it's a lot of text documents from movies and TV show episodes and so on. It's in many different languages, but the vast majority are English. And I've also got a separate database with around 20 gigabytes of lyrics, which is also many different languages and also shows a sort of broad variety of textual data. So here we have an example query where we've searched for a quote from Dr. Strangelove. "Gentlemen, you can't fight in here. This is the war room." And you can see how the query has been parsed. So within, since I quoted this, and since this is ran through the web search to TS query, you can see that it's added distance operators where it removed stop words that it didn't feel was relevant to the matching of the document. Here we have a search for a quote from the 60s Batman show that ended each episode. So this would match basically all the episodes of the 60s Batman show. Here I haven't used the quoting, so it's only stemmed the results and added the distance operators. It hasn't added distance between them, and yeah. And as another example, we have a Seinfeld quote, yada yada yada. And finally, we have, within the lyrics search, we have a quote from the Barbie Girl song by Aqua, which had a resurgence this year due to the Barbie film. And here is what that query looked like. One thing that's a bit different from the previous example is that I use what's called TS headline. TS headline shows which parts of the document were matched, so you can bold those parts. So if we go back here, you can see that the words that match the query have been bolded by the result. And usually, in TS headline, you can also specify how you want those bolded. So sort of, do you want them in Markdown style with just a star around them? Do you want them with HTML tags? How much of the document around the matched part do you want to show? So it's pretty configurable. Yeah. That was everything I had on full text search. So let's move on to some graphs and trees. Graphs and trees are traditionally thought of as pretty hard within relational databases. It's usually you would use a dedicated database like Neo4j or similar. But they can be done with a database feature that is called common table expressions, especially recursive ones. Probably, even if you've worked quite a bit with SQL databases, you might not have come across a common table expression. It's basically a subquery with a specific syntax. So it allows you to separate out subqueries into separate parts of the main query, which can help with readability quite a lot, and in some cases can be an optimization. But it's not really different in its base use case. But the interesting part about common table expressions is that they can be recursive. So in this example, I just have a common table expression that counts from 1 to 20. But it does this by iterating each loop and getting back the previous result and using that as the next iteration. And this example is not very interesting, but this allows you to traverse your data in ways that are not exactly common within relational databases. So let's talk about how we apply this to tree structures. And I'm hoping everybody is familiar with what a tree is, but you can see a visualization of one here. Usually it's just that you have a parent that's pointing to its children, and that can go on for an arbitrary amount of levels of depth. And the schema for a tree can be extremely simple. In this case, we just have a table called nodes. It has an ID, and it has a parent reference. And that reference is back to another node within the same table. And we've added a column where we can add some arbitrary data in JSONB format. And here we can all see how it can be queried. So we're basically having a starting point. That's the starting ID, and that's the top within the body of the CT. And then we have a union, and then we have a select statement that uses the previous ID. So the previous tree ID as its next point. And in a tree, you might want to query either going up in the tree or going down. So you can switch the comparison operator here to decide if you're going up or down. And as an example use case, I was working on a healthcare IoT solution. We had a tree of organizations and physical locations. So we wanted arbitrary depth and we wanted recursive permissions because a lot of different companies and different hospitals have different layouts of their both organization and also their physical layout. So we couldn't really decide on the depth for everyone. We needed the flexibility. And this is an example query from that. In that case, we created a helper function within the database. It returns a set of locations, which is the table type that we had the tree in. And the rest of the query is basically the same as before. But graphs are quite a bit more interesting, so let's move on to those. And a graph is shown as an example here. You basically have nodes that have relations between them, and they can have arbitrarily many, and they can also usually have some data within the relation describing what is the type of link between the nodes. It requires a little bit more. We need two tables. In this case, we have one table, still the nodes table. It has the same ID and data column, but it doesn't contain any references. We have a separate table called links that contains the reference between the source node and the target node, and can also contain data about the type of relation. An example query of this looks very similar as before. Basically, we're doing the same operation, but only on the links table and comparing source and target. And then we join in the nodes at the end when we've found all the relevant links for our query. For this, I also have a demo. I've loaded a database with around 3 million nodes, which represent either actors or directors or movies. And I have about 9 million links between these nodes, which are what actor worked on what movie, and the data within the links table is what role they had as an actor or what job they had if they were part of the production crew. So here I've run a query on Killers of the Flower Moon, which shows the first 100 nodes that are relevant to it. And I can recenter the graph on other nodes. So for example, if we click on Edward Scissorhands, we can see all the different people who worked on it and also what the structure of the social graph around them is. In this example, I've limited it to just 100 results, but we can probably go a little bit. Let's see if the demo gods are with me today. Yes. Here, I've ran the same query, but with 1,000 nodes. And you can see it becomes quite a bit more complex and also laggy due to my front-end graphing skills in D3 not being very good. But the actual database query is quite quick. So here is the query running in the background for that visualization. It's pretty similar to what I shown before, but we have some limits on it. So I use a couple of different CTEs, one recursive first to find the full graph, and then I have one that just limits the results from the graph. Then I have one that picks out the nodes that are relevant from the graphs, and then I do some JSON aggregation within the database in this case, just to return it in a nice format and not have to parse it within another backend languages. And then the main query, as you can see in the bottom, is basically just returning the results from the previous CTEs. If you want to play around with that, it's public on graph.e0.nu. It'll be live for a while. I don't know if it will be live for days, but you can try it out. That's basically what I had on graphs and trees. Let's talk a bit about documents. And when I say documents, I mean the sort of documents you would usually store in something like MongoDB. So this usually JSON documents and sort of arbitrary structure. So whereas in a normal relational data, we would have a pretty strict structure, in a document database, you usually have a bit more free form. And storing JSON in relational databases, it used to be very controversial. It probably still is to quite a few of you. But Postgres has excellent support for both querying and modifying JSON within the database, and even some document databases. So AWS Document DB is probably built on top of JSON columns in Postgres. I say probably because it seems to use the same Aurora backend and engine, but it's not confirmed or public. So yeah. And usually when I start to model a database, I start with a lot of JSON columns. I basically have relations between tables that have the primary data in a JSON column, and then I move them to separate columns, sort of parts of the JSON document, as is needed, and sort of as I find the shape of the data and what sort of queries I need or want to do against it. So simplest possible document store, very much like the key value store, only difference is that the value is now a JSONB column. Here we can add some example data. In this case, it's probably an employee roster with 2 different departments, accounting and sales. We have first name, last name, and age of all of the employees. And if we want to query this, there are some JSON-specific operators for retrieving data from within. have these same example tables as before, and I'll just show some quick queries via PostgreSQL on those tables. So a very simple example is just going to nodes, which is the table name, and requesting a specific ID. We're using EQ dot to mean equals, because we can have multiple different types of comparators there. We could have greater than, less than, and so on. We can also, of course, select specific fields. So here we've selected ID and data name. And the data name uses the same JSON operator as before. So those are also supported by PostgreSQL. And what's very nice is that PostgreSQL will auto-discover the relations within our database. So here we've selected links. It looks like a function call, but it's a join. And that will automatically join in all the data from the links that are related to that node. So we get everything out in one call. We don't need to do multiple round trips back to the server, which is extremely nice. And I mentioned row-level security before, because you probably don't want everybody to have the same access within your application. You probably want to do some stuff based on which user is logged in and so on. And for that, we use what's called row-level security, which is a PostgreSQL feature, not a PostgreSQL feature. So you can use this even if you don't use PostgreSQL. And it basically enforces an automatic check on each access to a row within the database. What's nice about this is it works automatically with joins and functions and similar. So you don't need to write the logic to check, okay, is all the data that I've joined in, is that supposed to be visible to my specific user? It basically declarative way to handle authorization. This example is actually just taken from the PostgreSQL documentation. And we have a table called accounts, which has a column called manager. And we only want the account manager to access these rows. So we have this alter table that enables row-level security on this table. And then we have a create policy that creates a specific policy to who can access the rows on this table. As is in the ID, which would be the ID of the current row. So this references the specific row that's trying to be accessed. And then we have a separate policy for deletions, where we just pass in an additional parameter saying we need this user to not just have any role here, we need them to be admin. And besides all of these use cases I've taken up here, we have excellent support for geospatial data via PostGIS, time series data via timescale, vector database queries via pgvector. So that would be similar to the full text search, but using more semantically aware and sort of machine learning stuff. We can do machine learning and AI models with ML. We can also do some interesting stuff with querying and joining in external data sources if we don't want to keep everything within Postgres. So there's support for other databases, basically all of them. Other Postgres clusters, you can do stuff like query your EMAP, so that's email, plain files, S3, just random HTTP endpoints. You can model all of this as one access pattern within your database. You can also write your own adapter for this. I've written one in Python. It was very easy, even though I'm not at all a Python programmer. And there's also built-in support for the primitives needed for message queues. That was going to be the next example, but unfortunately I don't have time for it. And there's much, much more. And you can, of course, get hosting for Postgres on all the major clouds. And there's Neon, which is serverless Postgres with Git-like database branching, which is extremely useful for testing, where you can branch off, run a test, and then destroy that branch. And that's run against the ecology. There's also Supabase, which is sort of like Google Firebase, but built on PostgreSQL and PostgreSQL. And it's extremely easy to get started with and get a full backend up in a couple of minutes. So my conclusion, I think Postgres is extremely reliable. It's become very performant, even though that wasn't its primary focus in the beginning, perhaps. It's extremely extensible, as we saw on the list of extensions available for different use cases. And since it supports many different use cases, you don't need to sync your data between different databases. So by this, I mean, if you had a stack with Elasticsearch and Redis for a cache, and then Postgres as your primary data, you need to make sure that all that data is synced, so that you don't get results from, say, Elasticsearch that references rows within Postgres that don't exist. So you get rid of those use cases, and you basically have a single data source that is reliable and consistent. Any questions? Otherwise, I think we're like 1 minute away from the official stop time, but go ahead. Yeah. So that sort of depends on how you compare them, since Redis has both a durable mode where it flushes to disk, and it has an in-memory mode. It also sort of depends on how big your cache size is, since Linux will cache the database pages that back that Postgres table. So I would say sort of in general, the performance I've seen is about maybe half of Redis. So it's fast, but it's not like extremely Redis fast. But plenty fast enough for most cache use cases I've seen. The question is more sort of, if you're getting up to a scale where that traffic becomes the heaviest part, that would of course also impact your database traffic, since you're using the same database for both. So that's more of a question. So I would say starting out with using this sort of within database cache solution, and then it's pretty easy to move that to, for example, Redis or Memcache or similar when that is needed by the scale. But sort of not building out that complexity before it's needed is in general what I recommend. Great, thanks.